All right, guys, so uh, today we are going to talk about groups and their reactivity. So I'm going to do an activity in our journal that I would be doing in class with you if I was there. So you can pause this at any time, and you can always take a second and go look at my journal that is at the front of the table on my desk to make sure that you are cutting it right. Remember, when it comes to interactive journal activities, when in doubt, stop and ask a question, because it's always easier to not have cut enough than to cut too far. Okay, so in our journal, we are going to go to the very last thing you did, which should, in your journal, if I'm not mistaken, be your C notes for the periodic trends. Okay, so once you're there, you need to turn your journal sideways. So I want the right side to be facing down and the left side to be up. Okay, you should then get a periodic table from Miss Moore that is already nice and cut for you. Now, I need you to take 4 pages in your hand. So 1, 2, 3, 4. Okay, so again, we're on the very first clean page on the right-hand side after your C notes from periodic trends. We turned our journal sideways, so the right side is facing down, and we took 1, 2, 3, 4 pages in our hands. Okay, with all 4 pages in your hand, I need you to move them up and out of the way, and I want you to glue your periodic table on that 5th page. So go ahead and pause the video and glue that now. Or you can do it while I'm doing this. Okay, so I'm going to go take those 4 pages that I folded and move them back down. Okay, so you're going to need some scissors for this. And this is where, if you're not sure, you can always pause the video, rewind it, or go get my journal to look at it as a reference to make sure that you are cutting the way you should be. If somebody's already using my journal, don't grab it from them. All right, so I'm going to take all 4 pages in my hand. And what I'm actually wanting to do, as this is the hard thing to try to show, is I want to look and see where group 1 ends. So we know that on a periodic table, a column is called a group. And so if I kind of look right here, I scroll up to the top, I can see that pretty much group 1 ends between my 3rd and 4th line. So I'm going to kind of make a mark out there and a mark towards the bottom. Okay, so between my 3rd and 4th line. Now, taking all 4 pages in my hand, I am going to cut. Let me see if I can move this up so y'all can see it. I'm going to cut, so I have 1, 2, 3. I'm between that 3rd and 4th line. Make a mark, and I'm going to cut over to that area, and then I'm going to, again, with all 4 pages in my hand, cut up. You might want to watch this before you do it, and then I will cut it off. So if you'll notice, through all 4 pages, I have cut, so I only now see group 1. So go ahead and do that now. All right, so once I've done that, just set your papers aside. Do not make a mess out of them. On the very top, we want to label this group 1. And then pick a color. It really doesn't matter what color to me. I feel like highlighters work pretty well. I'm going to highlight every element in group 1. Now notice I'm not going to highlight hydrogen because as we saw yesterday when we were doing the periodic table basics, hydrogen belongs to a group all to itself. It does not actually belong to group 1. And if you look at the periodic table I have in my room, you can see that hydrogen is actually above the 1, indicating that it doesn't belong to group 1. And then I'm going to take the same color and highlight group 1 so I know that these two colors go together. So group 1 is actually called the alkali metals. And it has some very, very interesting characteristics. And one of the things that they all have in common is obviously they are all metals. Okay? And because they are group 1, we know that that means that they have how many valence electrons? That's right. The answer should be 1. Every single element in this group has 1 valence electron. Now, remember that a valence electron determines reactivity. So that's what this whole video is going to be about. How can you tell how an element is going to react based on the number of valence electrons it has? So I'm going to give you a very loose example, and it's weird and it's crazy like all of them are, but it's really going to help you understand how elements react based on their valence electrons. So I want us to pretend that to make an atom happy, you want to have a full outer energy level. Okay, and we know that the outer energy level is where the valence electrons are. Now realize that no, atoms are not living, so they can't have feelings, but we're just going to pretend for this analogy. So to make atoms happy, they have to have a full outer energy level. Well, when you have 1 valence electron, that means you are 1 valence electron away from being happy. So if I was to draw a picture, look over here, and let's say that I'm going to draw lithium, I have 2 valence electrons and then 1 on the outside. 2 electrons and 1 valence electron. Notice that lithium is in group 1 right here. So if I was to lose this valence electron, if I was to lose it, what would happen? I would go down to my next energy level, which happens to be full, which would make me very, very happy. So the closer an atom is to having a full outer energy level, the more reactive it is, the more desperate it is. So it's almost like elements in group 1 are so desperate to get rid of that 1 valence electron that they will react with anybody. They're desperate. They're like, take it, take it, take it, take it, take it, take it. I don't want it anymore. Take it, I don't want that electron, take it. All right, they're desperate. So we consider them to be the most reactive metals. Okay? Now, I actually should be glad that I'm not in class with you because, I really act this out and get into it. All right, so this is a star. Very important. Group 1 is considered the most reactive metals. And again, why do we consider them to have the most reactive metals? Because they are 1 valence electron away from being happy. And what do they want to do with that 1 valence electron? They want to lose it. Okay? Now, another special property of alkali metals is they actually react violently with water. So if you were to take some pure lithium, pure sodium, pure potassium, and I'm pretty sure on YouTube you can Google and watch a video of it, but if you were to take any alkali metal and throw it in water, it violently explodes. And there are actually videos where they are taking, some like a piece of sodium that's probably like this big and throwing it in a gorge of water, and it is like a dynamite goes off. It is a huge violent reaction. And the reason why is because they all have that 1 valence electron. The moment it hits that water and it's trying to get rid of that reactron, that is a reaction. And it's making something new. But the whole process is those elements getting rid of that one valence electron. Okay? So any questions about alkali metals? They are group 1, which is lithium all the way to francium. They're all metals. They have one valence electron because they are group 1, and they are the most reactive metals because they are one valence electron away from being happy. All right, so take this page and turn it back. Okay? So now you should only have 3 pages in your hand to your periodic table. And what we're going to do is actually extend our cut to group 2. So if I look at group 2, I can see that it kind of ends in between my 4th and 5th line. So going back to my 3 pages, I'm going to kind of make a mark between my 4th and 5th. So taking my scissors, okay, I am just going to barely extend my cut. And I could actually kind of pull this back and check and see that that is plenty. Okay, so you're barely going to extend the cut. And again, this time you should only be cutting 3 pages instead of 4. Okay, so if I go back, notice I only see group 1. And when I fold it up, now I can see group 1 and group 2. So this is how this is going to become interactive. All right, so let's label this group 2. If I can find the right color I want. And then take a highlighter or a map color or a marker. Actually, don't use a marker. And highlight group 2 a different color than you highlighted group 1. Okay, and then highlight the title so I know they go together. Okay, so the name of group 2 is actually called the alkaline. So unlike group 1, which alkali, this is alkaline earth metals. So just like group 1, what are some properties of group 2? Well, again, they are obviously all metals. And because they are group 2, they have 2 valence electrons. And they still want to lose them. Now let's go back to that picture that I had of lithium. Okay? And let's turn it into beryllium. So now it's beryllium. It's in group 2 because it has 2 valence electrons. So we know that all atoms want to be happy to get that full outer energy level. They're all striving for that. Well, if an atom has 2, that's farther away from being happy than group 1. So how many valence electrons are they away from being happy? Well, the answer is 2. They want to lose both of these because it is a lot easier to lose 2 than it is to gain 6. Well, where did I get that number? Because remember, what is a magic number that they all want to get to? That magic number is 8 because that's what makes them full. So it's a lot easier to lose 2 valence electrons than it is to gain 6. But losing 2 is harder than losing 1, so we consider them to be very reactive metals. But notice, they are not the most reactive. So as we get farther away from being happy, our reactivity is going to decrease. The closer we get to being happy, it's going to increase. All right, so that's group 2. Alkaline earth metals, they're all have 2 valence electrons, and they are very reactive metals. All right, so turn the page. And now you should actually have only 2 pages in your hand until you get to your periodic table. And this time, we're going to completely go to the opposite side of the periodic table, and we're going to go to the right. So I want you to look and see where group 18 ends. So for me, group 18 ends almost on this second line, like right there. So with only 2 pages in my hand, I'm going to kind of note that that's where I need to cut to. So while cutting 2 pages, I'm just going to cut to that second line, and then I can check, and that looks great, and then I'm going to cut it off. All right, and there's group 18. And it's actually not showing enough for me, so I'm probably going to go back over and just trim it a little more. There we go. Okay, so group 18. And you should actually already know what the name for group 18 is called because you had to do it yesterday on your periodic table. They are called the noble gases. Okay, so picking another map color or a different highlighter, we are going to highlight every element, including helium, in group 18. Now, one of the questions on yesterday's activity was, why is helium included in the noble gases if it doesn't have 8 valence electrons? And the answer to that was, even though helium does not have 8 valence electrons like all the others do, it still has a full outer energy level. Because remember, to fit that first energy level is 2, and then everyone after that is 8. So it is still considered a noble gas because it still has a full outer energy level. Let's highlight this, the same color. Right? So what are some characteristics we could talk about noble gases? Well, obviously, they are all gases. And we know if they're all gases, that must mean that they're all nonmetals. Okay? But here is what is really special, and for some reason, and I don't know why, this is the STAR's favorite group to test you on. They love group 18. It's their favorite one because it does have that helium as an exception. One thing that the noble gases have is they are the only group that is completely unreactive. It is the only group that is completely unreactive, meaning they do not react with anybody. You will never find helium in a compound because it has a full outer energy level. And what did we say about that? That means that an element is happy. So if helium's happy, it's not going to risk reacting with another element and gaining and losing another valence electron and making itself unhappy. So it's going to stay by itself. So every noble gas is completely unreactive because they all have 8 valence electrons. Of course, except for helium, where helium has only 2. And VE stands for valence electrons. And we know that that's because they have a full outer energy level. Which means that they're happy. Okay, so we only have one more group to go. So take this page and fold it up. So you only have 1 page left to cut, and you are just going to extend the cut that you did on the left, or on the right, I'm sorry, and you're going to look and see where group 17 ends. For me, it ends on the 3rd line. So I'm just going to take this and extend it to the third and cut it off. So this will be the last cut you have to do. And this is group 17. And so pick your last map color or highlighter color and highlight that. Now, group 17 is actually called the halogens. And in Latin, halogen actually means salt makers, because what happens is if group 17 binds with an alkali metal, they make a salt. So what are some characteristics of group 17? Well, they are all nonmetals, but they're not all gases like the noble gases. Because they are group 17, they have 7 valence electrons. Now I want you to think about that. They have 7 valence electrons. So if we were to draw a picture of fluorine, how many valence electrons does it have? It has 7. So is it happy? Well, the answer is no, because it wants 8. It is 1 valence electron away from having a full outer energy level. And remember, we talked about the closer an atom gets to getting that full outer energy level, the more reactive it is. So the halogens are extremely reactive. However, they do not want to lose a valence electron like the alkali metals do. They want to gain a valence electron. And so because of that, we consider the halogens the most reactive nonmetals. And put big stars by that because that's important. Right? So just like the alkali metals were the most reactive metals because they were 1 valence electron away from being happy, the halogens are the most reactive nonmetals. So group 1 and group 17 have the same reactivity. However, group 1 wants to lose that where group 17 wants to gain. And we'll just add that last little bit is where they form a salt when combined with group 1. Okay, and the example is, let's do sodium chloride, NaCl, right? Well, Na comes from which group? Group 1. And chlorine comes from group 17. So, let me zoom in for a little bit. If you belong to group 1, how many valence electrons do you have? 1. If you belong to group 17, that means you have 7. What's 1 plus 7? Is 8, which is our magic number. So the whole reason certain elements bind together is because they're trying to make each other happy. They're trying to fill their outer energy level. So valence electrons are very, very, very important because they determine reactivity. So just like number of protons determine the identity, valence electrons determine reactivity. And I hope you understand that after doing this activity. If you're still a little confused on how valence electrons determine that, when I get back in class on Monday, I'll be happy to give you a workshop on it. Okay? But just know that these are the 4 groups that you are expected to know the names of and the characteristics. Okay, so to recap, you have group 1, alkali metals, the most reactive metals. Group 2, the alkaline earth metals, which are very reactive metals. And then we're going to skip to group 18, the noble gases, completely unreactive. And then group 17, the halogens, which are the most reactive nonmetals. And then Monday, we're going to talk about what the reactivity of 13, 14, 15, and 16 are. But I would like you to kind of think about if you could figure out the reactivity based on the number of valence electrons. Okay? So next to noble gases, could you figure out which group is the least reactive because they're so far away from being happy? So once you have this activity in your journal, go ahead and get with your group and start working on your superpowers for your superhero. And I'll see y'all later today. Bye.